Hey everyone, Victor is here, your organic chemistry tutor, and in this video I have a rather interesting synthetic problem for you. We are going to be starting from benzene and cyclopentane, but our product contains benzene and a long open chain with two carbonyls. So how are we going to accomplish this transformation? Well, the first thing that kind of jumps at us right away is that if we have a cyclic molecule and we end up with an open chain in our final product, we are going to be doing some sort of a carbon-carbon bond cleavage. And the most common bond cleavage technique that we know is going to be the ozanolysis, which is going to cut through the carbon-carbon double bond. Conveniently enough, we have two carbons over here that are carbonyl, which means that they could have been connected to each other in a cyclic molecule. Which means if I do sort of like a reverse ozanolysis in my retrosynthetic analysis here and connect these carbons 1 and 5 with each other, I would get an intermediate looking like this, where carbons 1 and 5 used to have a double bond between those. Now, if I take this double bond and I cut it using the ozanolysis reaction, I'm going to end up with my final product. Which means that we now need to figure out two things. First of all, how to create this bond between carbon number 1 and our aromatic ring, and then how to create this double bond between carbon 1 and 5. Well, let's look at the double bond first. Typically, we're going to be making double bond via some sort of elimination reaction. And in order to have an elimination reaction making a double bond, we need to have a leaving group. So there are two potential precursors to our alkene here, looking like this, where my X, my leaving group, can be sitting either on carbon number 1 or on carbon number 5. But I also do remember that I need to make this bond over here between my 5-membered ring and the aromatic ring, which means that if my X is an OH group, then I can easily make that bond via the Grignard reaction, which means that the bottom precursor, where the X is on the carbon number 5, is not the ideal precursor for me. So I'm going to go with the top one and ignore the bottom one. So let's just erase that so it doesn't clutter our picture. Now, making a tertiary alcohol while making a new carbon-carbon bond, well, that is a hallmark of the Grignard reaction. So we are going to go back again to our good old friend Grignard here, where our starting materials for that step are going to be phenyl magnesium bromide and cyclopentanone. So now the question is how we're going to make both of those intermediates from our starting materials. Obviously, we are going to be making our phenyl magnesium bromide from our benzene, and we are likewise going to be making cyclopentanone from cyclopentane. The synthesis of phenyl magnesium bromide is going to be a low-hanging fruit, so I'm going to start from there. I will begin with the benzene, and I'm going to treat it with bromine in the presence of iron bromide, which is going to be our catalyst in this electrophilic aromatic substitution in this halogenation reaction, which is going to give me the corresponding bromide, the bromobenzene molecule in this case. Then we are going to take our bromobenzene and we are going to treat it with magnesium in THF. It has to be a dry THF or dry ether if you like, which in turn going to give us the phenyl magnesium bromide that we need for our next step. But before we get to our next step, before we get to our Grignard reaction itself, we need to have our ketone. Well, synthesis of that one is going to be actually pretty straightforward as well. When we are starting with just a simple alkane or cycloalkane like in this case, so I'm going to take my cyclopentane, the only reaction that those guys are going to be able to do is the radical halogenation. So I'm going to use radical halogenation, something like just simple Br2 and light, and that's going to give me the corresponding bromide, which in this case is going to be bromocyclopentane. Then we know that in order to make a ketone, we need to have an alcohol, so we need to substitute that bromine with the OH group. Well, that one we can do by just treating our bromocyclopentane with water, and the replacement is going to happen via the substitution reaction SN1 style, giving me the corresponding alcohol. Now, in order to convert my alcohol to a corresponding ketone, what I'm going to do, I will oxidize that. So let's say we're going to use PCC in this case to convert that secondary alcohol into a ketone, and I will remind you here that conversion of a secondary alcohol to a ketone can happen regardless of which type of oxidation technique you are going to be using, because we cannot oxidize the secondary alcohol to anything but the ketone, so we can use PCC, we can use Swern, or you can even use Jones oxidation or chromic acid if you like. It really doesn't matter in this case. But now, once we have our phenyl magnesium bromide, the green molecule, and our ketone, the purple molecule, we can react those two together, which is going to result in the following alkoxide, which then of course we're going to treat with weak acid to protonate that. So let's say I'm going to just say that some sort of acidic workup, H3O plus workup over here, doesn't matter what sort of acid we are using here, for as long as it's a weak aqueous acid, it will do the trick. And we get our alcohol. Now, to go from the alcohol to our alkene, we are going to do the dehydration reaction. This is a simple dehydration of alcohol reaction, which is done E1 style in the presence of a strong acid. So we're going to use something like H2SO4 and heat, making my alkene. And the very last step in the synthesis is going to be the oxidative cleavage, where we're going to be breaking our double bond. Actually, when it comes to the cleavage itself, we're going to do the reductive ethanolysis because we want to preserve our aldehyde, but any kind of cleavage is in the oxidation reaction, so you could also call it an oxidative cleavage. So in order to do that, we are going to first treat our molecule with ozone, which is going to be O3, and then in order to preserve our aldehyde, we are going to do the reductive workup, which is the most commonly done with something like dimethyl sulfide, DMS, or alternatively, you could also use zinc and acid, so zinc and something like HCl. And there you get it. So this example, like one of my previous videos, uses the idea of the convergent synthesis, where we are first creating our key intermediates and then bringing them up together and then finishing up our synthesis overall. Is this the only way to accomplish this synthesis? Oh, absolutely not. There are many different ways how we can deal with synthesis, especially when it comes to more complex molecules. So if you have any other ideas how to accomplish this synthesis, let me know in the comments below and we'll talk about that. But that's all I have for today. Thank you for watching. If you learned something new today, as always, hit the like button and let me know about that in the comments below. Your likes and comments really help in promoting my videos and I really appreciate that. Subscribe to the channel for more organic chemistry updates and tutorials, watch this video next, and I will see you tomorrow.